Weird facts about SUPERCONDUCTORS. Welcome to the enigmatic realm of superconductors, where the laws of classical physics surrender to quantum mysteries. I'm Professor Ellis, and today we'll venture into a world where electricity flows eternally, magnets float in midair, and the impossible becomes possible. Prepare to have your understanding of reality challenged. What are SUPERCONDUCTORS? Imagine a material so extraordinary that electricity flows through it with absolutely zero resistance. Not minimal resistance, but truly zero. These aren't science fiction fantasies, but real materials that exist in laboratories across the world. Superconductors represent one of nature's most baffling phenomena, a doorway into quantum reality that materializes at macroscopic scales we can actually see. The quantum anomaly, what makes superconductors truly perplexing, isn't just their practical applications, but how they force us to confront quantum mechanics in the visible world. In your everyday experience, quantum effects remain hidden in the subatomic realm. But superconductors, they bring quantum weirdness right before your eyes, challenging our comfortable classical intuitions about how reality should behave. The accidental discovery, our strange journey, begins in 1911, in the laboratory of Dutch physicist Henk Kamerlingh Onnes. Having just discovered how to liquefy helium, reaching the astonishing temperature of just 4 degrees above absolute zero, Onnes was exploring how materials behaved in this unexplored temperature territory. The Mercury mystery. Onnes was measuring the electrical resistance of Mercury at these extreme temperatures when something utterly unexpected happened. The resistance didn't just decrease as the temperature dropped, it completely vanished. His instruments registered zero resistance. Thinking his equipment had short-circuited, Onnes checked everything repeatedly. But no, Mercury had entered an entirely new state of matter, one that had never been observed before. The DCADS-long puzzle, what Onnes couldn't have known, was that he had stumbled upon a phenomenon that would baffle the greatest minds in physics for decades. Even Albert Einstein and Niels Bohr couldn't explain it. It would take until 1957, nearly half a century later, before a satisfactory theory emerged. And even now, aspects of superconductivity remain shrouded in mystery. The Meissner effect, but the disappearance of electrical resistance isn't even the strangest thing about superconductors. In 1933, physicists Walther Meissner and Robert Ochsenfeld discovered something even more bewildering. Superconductors actively expel magnetic fields from their interior. This isn't merely blocking magnetism, it's actively pushing it away. Quantum levitation, this peculiar property, leads to one of the most mesmerizing demonstrations in physics, quantum levitation. When a superconductor is placed near a magnet, it doesn't just repel the magnet. It locks into position in midair, suspended by invisible quantum forces. It can even glide along a magnetic track, seemingly defying gravity in a way that appears magical even to trained scientists. Perfect diamagnetism. What's happening is perfect diamagnetism. The superconductor generates precisely the right electric currents on its surface to create a mirror-image magnetic field that perfectly cancels the external field. These aren't approximate calculations, they're perfect. Nature somehow knows exactly what currents to generate for perfect cancellation, a precision that hints at deeper quantum coherence. The dance of Cooper pairs. Now we descend into the quantum abyss. In normal materials, electrons repel each other due to their identical negative charges. But in the superconducting state, something preposterous happens. Electrons actually pair up, forming what we call Cooper pairs. Quantum entanglement, these Cooper pairs aren't just physically close. They become quantum mechanically entangled. Electrons that should, by all classical logic, repel each other instead move in perfect synchrony, connected by quantum threads that transcend space in ways that defy our intuitive understanding of reality. The BCS theory, the Bardeen-Cooper-Schrieffer theory, finally explained this phenomenon in 1957. The key insight: the electrons aren't pairing directly with each other, but interacting through vibrations in the crystal lattice called phonons. It's as if the crystal itself mediates a quantum attraction that overpowers the electrical repulsion, allowing electrons to form these bizarre quantum partnerships. The temperature enigma for decades, superconductivity required temperatures close to absolute zero, impossibly cold for practical applications. Then came the shock of 1986. Materials that superconduct at temperatures as warm as liquid nitrogen, 77 Kelvin or minus 196 degrees C. While still extremely cold, this was revolutionary, making superconductivity hundreds of times cheaper to achieve. The high-temperature puzzle, these high-temperature superconductors, remain one of physics' greatest unsolved mysteries. Unlike conventional superconductors, which are well understood, these copper oxide-based ceramics follow different rules that continue to perplex researchers. Some believe understanding them completely may require entirely new physics beyond our current theories. The LK99 controversy in 2023, claims of a room temperature superconductor called LK99 briefly sent shockwaves through the scientific community. Social media filled with amateur scientists attempting to reproduce the results, creating a moment of scientific pandemonium. While these specific claims didn't hold up to scrutiny, they illustrate humanity's relentless quest to unlock this elusive phenomenon at everyday temperatures. Superconducting qubits, the quantum coherence exhibited by superconductors, makes them ideal for quantum computing. Superconducting loops can exist in quantum superpositions, simultaneously carrying current clockwise and counterclockwise, a macroscopic manifestation of Schrödinger's infamous cat paradox, both alive and dead at once. Maglev trains imagine trains that float above their tracks, eliminating friction and enabling speeds exceeding 600 kilometers per hour. This isn't speculative technology. Japan and China have built such trains using superconducting magnets. You're literally riding on quantum effects when you board these marvels of modern engineering. Squids, quantum sensors perhaps most astonishing, are squids, superconducting quantum interference devices. Sensors so sensitive they can detect the minute magnetic fields generated by a single neuron firing in your brain, or map the magnetic field generated by your heart with incredible precision. These devices can even detect magnetic fields millions of times weaker than Earth's magnetic field. Unsolved MYSTERIS, despite a century of research, superconductivity still harbors profound mysteries. We don't fully understand high-temperature superconductors. We haven't achieved room temperature superconductivity. And strange variants like topological superconductors may hold keys to entirely new quantum technologies, including fault-tolerant quantum computers. The quantum future, as we conclude this uncanny journey, consider that superconductors reveal something profound about our universe. The quantum world isn't just a theoretical abstraction for physicists to ponder. It manifests in tangible ways that can transform technology and our understanding of reality itself. The perfect conductivity, the levitation, the quantum coherence all point to a deeper order in the cosmos, waiting for us to unravel its secrets. Thank you for venturing into the quantum labyrinth of superconductors with me today.